In the today's class, I will discuss about energy density in electrostatic fields. Actually, what is energy density? Energy density is calculated with respect to volume of the space in which these charges are assembled. Okay, whenever the charges are assembled in an empty space, energy will be present in the assembly of charges. Okay, for example, if we assemble Q1, Q2, Q3 and so on, Qn, then there is a energy will be present in this assembly of charges. But how to assemble them in the empty space? We'll see now. For assembling the charges in the empty space, some work is to be done for moving the charges from infinity to the empty space. Okay, let us consider three charges Q1, Q2 and Q3, and let us try to assemble them in the empty space. Okay, let this be empty space. Okay, no charge is available in that. Now let us move one by one. Consider three charges and move one by one to this empty space, and let us find out the work done in moving these three charges to this empty space. Okay, that work done will be equal to the energy stored in the assembly of charges. Let us consider Q1 first. Q1 from infinity to this place P1. Let us move this. Since there is no charge present in the empty space, there won't be any obstruction to this Q1. No electric field will be there in the empty space. The Q1 can be easily moved to this empty space. Okay, so work done will be 0. Work done due to moving of charge Q1 from infinity to this position P1. So W1 will be equal to 0. When it is moved, Q1 is available here. When Q1 is available, electric field will be generated due to Q1. Now let us move to this position P2, charge Q2 from infinity. For moving this Q2, some work is to be done on this Q2. Why? Because of the presence of Q1, a potential will be there at this point P2. Because of Q1, a voltage, the electric potential will be developed at the point P2. So work required to move Q2 from infinity to P2 is Q2 into, that is W2 is equal to Q2 into V21. That is V21 is the potential due to Q1 at the point 2. These are the points of position 1, position 8, position 2. The electric potential due to Q1 is V21 into charge that is to be moved from infinity to this position. And in order to move Q3, first we have to find out the potential at this point. Potential at this point 3 due to Q1, let it be V31, and due to Q2 is V32. So work required to move this Q3 from infinity to this point P3 is Q3 into potential at this point due to Q1 and Q2. Due to Q1 it is V31, due to Q2 it is V32. Okay, so W1, W2, W3. Total work done in moving these three charges Q1, Q2 and Q3 from infinity to these positions. That is WE is equal to W1 is 0 plus W2 is Q2 into V21 plus W3 is Q3 into V31 plus V32. If in the reverse order, if you move the charges, that means first you move Q3, then Q2 and then Q1, then work will be, total work will be, let us see now, if we want to, let us move Q3, then what is W3? W3 will be 0 because initially it is empty. Initially it is empty. Okay, so we can easily move Q3 from infinity to the position P1. Okay, for moving Q2, because of the presence of Q3, a potential will be developed at point P2. That is nothing but V21. So V21 in the reverse order, the W3 will be 0. Okay, W3 will be 0 and W2 is equal to Q2 into potential at this point is V. This is P3, this is P2 and this is P1, let us say. So potentially at this point P2 is due to Q3, that is V23. So this is equal to Q3 into V23. Then W2 is equal to W2. So W3 is equal to 0, W2 is equal to Q2 into V23. Okay, then W1, because of charge Q1 we move from infinity to this position P1. Here we have already moved Q2. So the potential at this point is V12 plus V13 into Q1 will be the work done. So Q1 into V12 plus V13. Okay, let us add these two expressions and divide it by 2 to get the total work done in moving charges Q1, Q2 and Q3 to the empty space. Then W2WE is equal to Q1 into V12 plus V13 plus W2 Q2 into V21 plus V23 plus Q3 into V31 plus V32. So work done is equal to this work done in moving these three charges from infinity to that empty space is equal to this expression is equal to Q1 into V1, where V1 is equal to total potential at P1 plus Q2 into V2, that is total potential at the position P2 plus Q3 into V3 by 2. This is the total work required to move charges Q1, Q2 and Q3 from infinity to the empty space. Okay, that is, this can be written as WE is equal to sigma K running from 1 to N QK VK 1 by 2. Okay, this is the total energy present in the assembly of charges. Here we have considered only 3 charges. So the total energy required to move from infinity to the empty space is equal to 1 by 2 sigma K running from 1 to N QK VK. If there are continuous charges, that is with the line density, surface density, volume density, those can be dealt with by using integral. That is work energy required for moving a line charge, that is rho L into V into dl. That is line charge, for line charge, for line charge. For surface charge, the work done is equal to rho s into V, rho s into V into ds. That means if we integrate this, we will get work done. That is rho s into ds will give a charge only. Charge into voltage, electric potential gives the work done. Okay. If there is a surface charge, if there is volume charge, integral rho v into v into dv. We will deal with this for work done in moving a volume charge from infinity to that empty space. We'll consider this and do the and find out the energy density by considering this volume density. Okay. That is work, that is the energy required to move this volume density. That is volume density, this charge. So according to Gauss law, the charge, the, the electric flux lines leaving surface is equal to d dot ds. D dot ds is equal to charge enclosed in the surface, that is rho v into dv. This is the Gauss law we have already covered in the earlier classes. This is what flux leaving the surface, d dot ds is equal to rho v into dv as per Gauss law. Gauss law. Okay, and rho d dot ds is also equal to integral del dot d into dv. According to divergence law. This is according to Gauss law and this is according to divergence theorem. According to divergence theorem. According to divergence theorem, integral d dot ds is equal to integral del dot d into dv. So from these two expressions are equations. Rho v is equal to del dot d. Rho v is equal to del dot d. These two are equal. Okay, so we can equate rho v and del dot d. So let us substitute this rho v here now in the above equation. So this work required to assemble the charges in the empty space, WE is equal to integral, what is rho v? Del dot d into V. V is what? V is voltage potential, electric potential into dV. Into dV. for a vector A and a scalar V, the identity is del dot VA is equal to A dot del V plus del dot A into V. Del dot A into V. In this identity, put A is equal to D. A is equal to D. Then this expression will become del dot V D del dot VD is equal to D dot del V plus del dot D into V. Okay, this del dot D into V, this can be substituted. That is del dot V from this expression, del dot D into V is equal to del dot VD minus D dot del V. Okay. So this D dot del V, del dot dV can be substituted here now. So WE, that is total work done, is equal to, let us substitute now, this here 1 by 2 is there. So del dot VD integral 1 by 2 minus D dot del V integral 1 by 2 into dV. Del dot D into V dV to dV. According to Gauss law, that is D dot ds is equal to del dot D dV. Okay, according to Gauss law, D dot ds is equal to del dot D dV. Now let us find out del dot dV. Del dot dV is equal to what? Integral del dot dV will be equal to V D dot ds. Okay, so in place, so let us substitute this now. This del dot dV into dV, there is nothing but this one. In place of that, let us substitute this Vd dot ds. Vd dot ds. So this is equal to, total work done is equal to 1 by 2 integral V into D dot ds, V D dot ds minus 1 by 2 into integral D dot del V dV. Actually, the energy density is nothing but work done per unit volume. Energy density is nothing but work done per unit volume. So this work done, total work done is equal to, since this D is proportional to 1 by r square and ds is proportional to 1 by r square, So therefore this term will tends to 0, is negligible, so it tends to 0 minus 1 by 2 integral d dot del V into dV. This one will remain. That is the total work done. W E is equal to minus 1 by 2 integral d dot del V dV. We already derived an expression that is E is equal to electric field is equal to minus del V. So let's substitute that. WE is equal to 1 by 2 integral d dot E dV. This is the final expression for work done, total work done. Now differentiating this with respect to volume now, we will get energy density, that is total work done per unit volume, that is dWe by dV is equal to 1 by 2 dE. This is nothing but this is equal to small WE, that is energy density is equal to half dE, and we can substitute D is equal to epsilon E, so it can be written in terms of E or D. So this energy density is equal to 1 by 2 D is equal to epsilon E, so we will get epsilon E square or of E is equal to D by epsilon. So D into D by epsilon, so which is equal to of D square by epsilon. So this is the total energy density, that is the total work done per unit volume. The energy is measured in joules. So energy density will be joules per unit volume. So units are joules per meter cube. We'll do one numerical on this. The point charges minus 1 nanocoulomb, 4 nanocoulombs and 3 nanocoulombs are located at coordinates 0, 0, 0, and the second one is located at 0, 0, 1, and the third one is located at 1, 0, 0 respectively. Find the energy in the system. Energy means work done in assembling these charges in the empty space. So we are going to find out the energy required to assemble them, not energy density, only energy required. So let this be empty space. Q1 is what? Minus 1. So minus 1 nanocoulombs from infinity to this position P1. What is this? What are the coordinates? 0, 0, 0. Let this be P1. So without spending any energy, this charge can be moved to that point P1. So once it is moved, it is available here. Minus 1 is available here. Charge is available. So it develops a electric field. Due to electric field, electric potential will be there at P2. At P2, what are the coordinates of P2? 0, 0, 1. 0, 0, 1 are the coordinates. So we have to find out the potential at this P2 and then multiply with the charge. That is, what is the charge? This is Q1. That is Q2 is 4 nanocoulombs. This should be moved. So Q2 into the potential at that point. So the work energy required is W1 is 0. W1 for moving this Q1, W1 is 0. W2 is for moving the W2, Q2 into V21. Q2 into V21. So let us calculate this Q2 into V21. So what is V21? V21 is equal to V21 potential at this point K into Q1 by K into Q1 by R1, which is equal to K is 9 into 10 to the power of 9 into Q1 is minus 1 by R is 001 minus 00. 001 minus 000, which is equal to 9 into 10 to the power 9 minus 1 by this is equal to 001 vector, and its magnitude is minus 9 into 10 to the power of 9 by root of 0 square plus 0 square plus 1 square, that is 1, which is equal to 9 into 10 to the power of 9. That is V21. So what is W2? W2 is equal to Q2 into V21, which is equal to, what is Q2? 4 nanocoulombs. 4 into 10 to the power of minus 9 into V21 into V21. Let us multiply this with this into minus into minus 9 into 10 to the power of 9. 10 to the power of 9 minus 10 to the power of 9, which is equal to minus 36. Minus 36 nanojoules. Nanojoules. And what is W3? W3 is equal to, well, you should find out the potential at this point, P3. Potential due to P1 and potential due to P2. So potential due to P1 is V31. V31 is equal to Q1 into K into Q1 by 3 coordinates are 1, 0, 0. So this is a position vector, magnitude is, let us find the first position vector, 1, 0, 0 minus 0, 0, 0. So which is equal to K into Q1 by 1, and V32 is equal to K into Q2 by this vector 1 minus 0, 0 minus 0, 0 minus 1. So we will get root 2. Magnitude is root 2. So W3 is equal to Q3 into Q2 Q3. Q3, which is equal to 3 nanocoulombs. So just you multiply now Q3 into nanocoulombs to the power of minus 9 3 into Q3 into V3 to V31 plus V32. So let us take K outside. Q1 is what? Minus 1 by 1 plus Q2 by root 2. Q2 is 4 by root 2, which is equal to 3 into 9 into 10 to the power of 9 into minus 1 plus 4 by root 2. So finally this total energy WE is equal to, add up, 13.37 nanojoules. This is the answer. Okay, with this energy density is over.